Hi guys, Audrey here. It is time to learn the elusive method 2. And in the process, we're going to do a case for partial fractions problem. So this is clearly a rational function. The derivative of the denominator is not the numerator, because in fact, we can even see that the degree of the numerator is equal to 3. And the degree of the denominator here is actually 5, because we're doing x squared squared, so that gives us a 4, that we're then multiplying by x. So the derivative of the denominator would have degree 4, so clearly that numerator is not it. So in our first step, we just say no division necessary. And then in our second step, we want to factor the denominator, but we can see that it's already factored, that x squared plus 1 is a sum of squares. We know that a sum of squares does not factor, so this is already factored. So really our partial fractions here is starting at step 3 with our partial fractions decomposition. So I have 1 minus x plus 2x squared minus x cubed all over x times x squared plus 1 squared. And what I see here is I've got this linear factor x, and then I have this quadratic factor x squared plus 1 that occurs 2 times. So what that means is this is a case for partial fractions because we have a quadratic factor occurring multiple times. So case 4. And so how we deal with that is we have our x in our denominator. It's just linear, so we have that constant on top, plus x squared plus 1 squared has a factor of x squared plus 1 in it. So we have x squared plus 1. We want our degree to be less, so that's bx plus c. And then we have x squared plus 1 squared. Again, we're thinking of this as that quadratic factor x squared plus 1. So we still just have a linear polynomial on the top, so dx plus e. So this is our partial fractions decomposition. So moving on to step 4, we multiply both sides by the original denominator, so by x times x squared plus 1 squared. And here I end up with 1 minus x plus 2x squared minus x cubed is equal to a, the x cancels out, the x's cancel out, x squared plus 1 squared, plus bx plus c. The x squared plus 1's cancel out. Only one of them does, which means I have an x left over, and I have an x squared plus 1 left over. And then plus dx plus e, the x squared plus 1 squared, both of those cancel out, and I only have an x left over. Now, we're going to start with method 1. We always want to start with method 1. If there are zeros in the denominator, we should plug them in because we're going to immediately start off by having one of our numerators, and that's going to be helpful. So my zeros here, the only one I have is x equals to 0. So I'm going to have 1 minus 0 plus 0 minus 0 is equal to a times 0 plus 1 squared. So that's a times 1 plus 0 plus 0. And I get that a is equal to 1. So here we started with method 1. And you'll notice that really we almost never use method 2 entirely by itself. The only time I could imagine using method 2 only the whole way through would be if you have a case for question that doesn't have anything else. So all of your quadratic polynomials are occurring more than one time, which means that the denominator has no zeros whatsoever. So we'll just say that here. Only makes sense to use only method 2 if the denominator has no zeros. Okay, so now we are going to switch to method 2. And method 2 is what's called the method of equating coefficients. So this is the method of equating coefficients. And what we do is we recognize that on both sides here, we actually have a polynomial. And therefore, those polynomials should be equal. So what I'm going to do is expand everything and try to figure out what is the coefficient of x squared? What is the coefficient of x cubed? What is the coefficient of x? And use that to answer this question. So let's see what I mean. So here I'm going to have 1 minus x plus 2x squared minus x cubed is equal to a, which I know is 1. So I'm just going to immediately replace that a with 1. Then times, I'm going to expand that polynomial. So this is x to the 4th plus 2x squared plus 1. I'm going to expand this kind of piece by piece. So I'll have here bx plus c times x cubed plus x, then plus dx squared plus e. Now we'll have that this is x to the 4th plus 2x squared plus 1 plus bx to the 4th plus bx squared plus cx cubed plus cx plus dx squared plus e. So now what I'm going to do is say these polynomials right here are equal. And so what that means is the coefficients of the associated powers should be the same. So I'm going to do one more thing here. So here I am expanding. Now I'm going to keep this the same. I'm not touching my left side. Minus x plus 2x squared minus x cubed is equal to, so I see that my highest power here is x to the 4th. And with x to the 4th, I have an x to the 4th and I have a bx to the 4th. So I'm going to write that x to the 4th, and the coefficient should be 1 plus b. So I'm just taking the coefficients, I'm adding those things together. Then we'll move on to the x cubed. And I actually notice here that I only have 1 x cubed, that's cx cubed. So I'm going to write it this way, plus x cubed times c. Then plus, what's going on with x squared? So we're going to look at our coefficients for our x squared here. And notice I have a 2x squared, and I have a bx squared, and I have a dx squared. So what that means is down here, this is going to be 2 plus b plus d. And then I'm going to look at x. Let's find another color here. I guess we'll do this. So x, I only have cx. So, or actually, I have c plus ex, my bad. It would appear that I forgot to write that x there. Sorry about that. So c plus ex. So then this x is being multiplied by c plus e. And then lastly, the constant. So here this is plus. The only constant I have here is 1. Good news, because that is also the constant that I have over on the other side. Now the reason that constant is 1 is because I already solved for a. So like otherwise that would have been a, just to kind of point that out. So the constants are the same, good news. So now I'm going to equate my coefficients. Equate coefficients. And what that means is I'm going to look at my highest power there, that x4. And on my right side, I have a b plus 1. But on my left side, there is no x to the 4th. So this is like I'm multiplying x to the 4th times 0. So b plus 1 should equal to 0. So this is the right side coefficient. And this is the left side coefficient. So here I'm going to get that b is equal to -1. Then I'll move on to x cubed. So on my right side for x cubed, I have a c. And on my left side, I have a -1. So actually, I just get immediately that c is equal to -1. So then I'll move on to x squared. And x squared, my coefficient on the right side is 2 plus b plus d. And on the left side, it's 2. So this gives me that b plus d is equal to 0 if I subtract 2 from both sides. But I already know that b is -1. So I can replace that b here with -1 plus d is equal to 0 and get that d is equal to 1. Now I'm going to move on to x and do the same thing. So my x coefficient is c plus e. So I have c plus e on my right side, and on my left side, it's -1. So c plus e is equal to -1. But I also know that c is equal to -1. So here I have -1 plus e is equal to -1, and I get that e is equal to 0. Now, if I had a constant term, I would do the same thing. This time my constants are both just 1, so I get 1 is equal to 1. And notice that I was able to easily solve for all of my numerators that way. Now, sometimes in method 2, notice that like I got c plus e is -1, 2 plus b plus d is equal to 2, and it was straightforward because I'd already easily solved for b and c. Sometimes, like we saw before, you are going to have a system of equations that you're going to have to solve. Okay, so let's finish up this problem now. We can move on to step 5, which says to rewrite the integral. So we can get that this is equal to the integral of a, which we said was 1, and my a was over x plus bx plus c, so that's -x minus 1 over x squared plus 1 plus dx plus e. Well, e is 0, so this is actually just x over x squared plus 1 dx. X squared plus 1 squared, my bad. All right, so now we have these 3 different things. And what we have here is something that we've already seen. We know that when this particular form occurs, we want to distribute that to the 2 things in the numerator. So I'm going to separate this into 3 different integrals. So I get the integral of 1 over x dx. That's really simple. And then, oh, actually 4, my bad, 4 different integrals. And then I'll have minus the integral of x over x squared plus 1 dx. And then minus the integral of 1 over x squared plus 1 dx. And then plus the integral of x over x squared plus 1 squared dx. Okay, this is a known form. This is a known form. And both of these other ones are just simple substitutions. So let's go do those on the side. For star, we'll let u equal to x squared plus 1. So du is equal to 2x dx. So I end up with 1 over 2, the integral of 1 over u du, which is 1 over 2 natural log of u plus c. So this is 1 over 2 natural log of x squared plus 1 plus c. And then my asterisk here, we're letting u be the same thing. And du is 2x dx. So we have the same u for both of them. Multiplying by 2, dividing by 2. And I end up with 1 over 2, but this time I have 1 over u squared du, which remember we want to think of as u to the -2 du. And this gives me -1 over 2 u to the -1 plus c, -1 over 2 x squared plus 1 to the -1 plus c. Since the other 2 things were known forms, we're not done with this problem. So I get ln of x minus 1/2 ln of x squared plus 1 minus arctan x, because that was x squared plus 1. We just have x. I don't have my a is 1. And then minus 1/2 times x squared plus 1 to the negative 1 plus a constant. So it's a minus there because even though it's a plus up here, my asterisk gave me a negative answer. All right, so this is my final answer to this question. It kind of was a really long question, and these case 4 questions are often really, really long. They can be worse. Maybe you're asking yourself, what would have happened if E had not been 0? And the answer is trig sub would have happened. So we're going to do that example. If E was not 0, what would we end up with in terms of an integral, and how would we deal with that? We'll do that in the next video. For this video, that's all. I just kind of want to like go through the steps here. We applied our partial fractions to case 4, but when solving for the numerators, we did the method of equating coefficients, which meant that I found the coefficient of every single power of x on the right side and then set it equal to the coefficients on the left side. So we're setting right side coefficients equal to left side coefficients. All right, so that is all for this video. I hope you enjoyed this intense problem. Bye.